All right. So I wanted to finish talking about recurrence relations and then start talking about languages. Questions on the homework, first of all. First of all, has everybody turned in their homework?
Yes.
All right, questions on the homework. Your quiz Friday will be on combinations and permutations and counting and pigeonhole principles. So if there's things you weren't sure how to do on the homework, we should work on them today and make sure that they're nailed down. Who integrated Java? Awesome.
Can you do the problem? It was the 3 points.
Yeah, the plane and the
Yeah.
points.
That's a fun problem.
I think
Do you remember the number in the section?
it was 2.4. I think it was 13.
Okay.
Okay.
There it is. Yeah.
It's the first time plane occurs in the text. 10 points in a plane. No 3 on the same. I don't know why they labeled them up to PN instead of P10. But that's okay. It's a free book. P1 through PN on a plane. No 3 on the same line. And how many lines are determined by the points? So let's just do P1 through P6. No 3 are on the same line, okay? So how do we get a line out of points? What do we do? Just connect them, right? If you have any 2 points, you get a line, right? So we could pick any 2 points. Well, which 2 points should we pick? We got 6 points to choose from.
Can't see.
Oh, man. That was like a fantastic drawing, too. We got 6 points. Which 2 points should we use to draw a line through?
P1 and P2.
P1 and P2, okay. There's a line. Are there any other pairs of points we could have picked?
Oh, yeah.
Like
P3, P4.
P3, P4. All right. Any others?
P6, P5.
P6, P5. So anytime that we pick 2 points out of these 6, anytime we choose 2 points out of these 6, we get a line, right? So how many ways can we choose 2 points out of 6? 6 choose 2, right? That's what that means. This is the number of 2 combinations of 6 items. That is the number of ways you can choose 2 things out of 6. And for each choice of 2 things out of 6, we can draw a line between them. We've got a line. Since we know that no 3 points are collinear, any 2 points we pick will give us a different line from any other 2 points. That's what the not having 3 things in a line means for us. So for 10, we would have 10 choose 2 different lines. And once you've done that, now how many triangles are determined by the points? Well, how do we make a triangle? Pick 3 points, right? So choose those 3 points or choose these 3 points, right? So the number of ways that you can choose 3 points out of 10, that's the number of triangles. So it's just 10 choose 3. So there's a spiffy geometric application of this stuff.
We really messed up that whole drawing.
Yeah. All right, other questions?
I think there was one about the basketball team.
Yeah. wouldn't call it a basketball team.
Oh, I know what he's talking about.
Yeah, it was where you had to pick a particular player for.
Yeah. The 3 center one.
Do you know what question number?
I think. Yeah.
Was it forward, not center?
Oh, maybe that's my problem.
Between sections 1 to 9.
Oh, good, good, thank you.
It was.
Might be 2.2, number 17.
I just like killed my thing. I can't get past this page. Yeah, we're done with the course.
Is it?
Yeah. So I'm viewing it in some kind of strange modality. All right, well, I just broke PDFs. Okay, how many ways can the coach at Tall U fill the starting positions on a basketball team of each team? If each of his 15 players can play any position. So you have 15 players to choose from. You have to know that a basketball team takes 5 players. So you have 15 players in 5 positions. So how many ways can you choose 5 people from 15? And it depends if the order matters or not, right? So, so on a basketball team, the order of the positions is significant, right? You're not just picking 5 people, you're picking somebody to play this position, somebody to play that position, and so on and so forth. So, so this sounds like a permutation question, right? Number of ways you can pick 5 out of 15, paying attention to the order. So 15 factorial over 10 factorial. Really tiny print that I don't seem to be able to make larger because I'm in like this fancy viewing mode. But part B says, what if in the answer the center must be one of 2 people? So we have a particular position that we have to put in one of 2 people for. So let's just say the first position has to be one of 2 people. Okay, go back, product rule, sum rule, right? The task of filling in the roster for this basketball team is a succession of 2 tasks. Task 1, pick the center. Task 2, pick the other 4 positions. Okay, how many ways can we pick the center? We're told there's only 2 people who can play that position, so there's 2 ways we can fulfill that. After we've picked the center, we have 14 players left. We have 4 positions we have to fulfill. Number of ways we can do that is number of 4 permutations of 14 players, which is 14 factorial over 10 factorial. So multiply those together, and it's 2 times 14 factorial over 10 factorial. Good thing to note here, when you're doing these questions, particularly on an exam, I strongly recommend, if you're going through this process, leave your answer first as something like 2 times p 14 comma 4, right? Make that somewhere prominent. And then, you know, equals 2 times 14 factorial over 10 factorial equals blah, 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 equals some final number. keep all of those steps in there. Because if you're pounding this out on a calculator and you get the final answer wrong and all I see is a number and it's not right, you don't get points, okay? If you've got this down, you've got probably 90% of the points, right? Because that's what I'm interested in. Do you understand that this is a product rule 2 and the permutations of 4 taken from 14, right? That's the money right there. You got that, I'm happy, okay? You mess up calculating 14 factorial over 10 factorial, that's just math. I'm not worried about that. So keep your work in there. Hi, whoever said hi. Keep your work in there, okay? Yeah.
I'm not sure if you understand this. Is it necessary to do the permutation computation to get the combination?
So we have a formula for combinations, which is just n factorial over n minus r factorial times r factorial. Right, and if you're trying to find number of you know, r combinations of n objects, you can just use this formula directly. Right, but what you're doing is you're actually calculating the number of permutations and dividing by the number of arrangements. But no, you don't need to go through that intermediate step. Right, all you got to do is use that formula, get your answer out. All right, other questions? I'm bummed out that I broke my PDFs. I've got 2 options of settings here, which are not the same. And somewhere in there, there's an option for making this work. Hey, I found it. All right. All right, good. All right, so short quiz on Friday. I'll probably start at 12:40, like 10 minutes after class starts. And I'll give you a half hour, but it'll be the counting stuff we've been doing in this unit. All right, so let me wrap up recurrence and recurrence relations with a story. So how do I want to do this? I'll fake it somehow. So how many people here are familiar with Towers of Hanoi? All right. So there's a story which describes a cave where there are some monks, and these monks have a pile of jade discs, and there's 64 of these discs, and they each have a different diameter. I have the wooden version, which is a step up from the cut-up pizza box version I started with when I first started teaching. And a student, after they graduated from Clark, they came back and they gave me this version of Towers of Hanoi. So we have these wooden discs, and let's just imagine we have 3 discs here. So they have different diameters, and the idea is your goal is to move the discs from one post to another. And the rules are the following. You're allowed to move 1 disc at a time only. So you can't just pick up the whole pile and move it. You can only move 1 disc at a time. Every disc has got to sit on top of either a larger disc or nothing at all. So I can put this over here because there's nothing over there. But I can't take this bigger disc and put it on top of a smaller disc. That's not allowed. And the goal is to move the pile from one post to another. And these monks apparently are in a cave, and they have these stack of 64 J discs, and they're moving these 1 disc at a time, following these rules. And when they finish moving the last disc and have moved the whole pile to another post, supposedly the universe will end. Okay, so that's marking the age of the universe. So let me show you a simple case, which is just two disks. And let's say I want to move these two disks from here to there. So it's not too hard. I can move this small disk out of the way, and then move the big disk to the middle, and then move the small disk on top, and I'm done. So mini universe just ended. If you have three, it's a little more complex, but I can move one here, move one here. Are you counting how many moves it takes? And we're done. Okay, in case you weren't keeping count, that took 7 moves. The previous one took 3 moves. If you have just a single disk, how many moves does it take? It's just 1. Okay, so how do we do this? Suppose I've just shown you that I can solve this puzzle for 3 disks, right? So if you got 3 disks, I just showed you how to do it. And if you don't know how to do it, you can come to me and say, can you move these 3 disks, and I'll be happy to do it for you. Suppose somebody comes up to you and says, hey, I'll give you $1 billion if you can move those 4 disks from one place to another. And you have no idea how to do it. But you know that I can move 3 disks. Here's what you can do. Hide this bottom disk. Come up to me and say, hey Nick, can you move these 3 disks from here to here? And I'll say, yeah, I can do that. I got office hours right now. So I'll go ahead and I'll move those 3 disks, and it'll take me 7 moves, and I'll put them over there. And then you come along and you take that biggest disk and you just move it to the middle. And now you say, hey Nick, one more question. Can you take these 3 disks and move them from this post to this? Well, all of these are smaller than this, so this doesn't affect my solution. I can just use my usual technique of moving those 3 over to there. And now you've moved all 4 according to the rules, and you get your $1 billion. So what happens? What happens if you have 5 disks? Can you figure out how to move 5? You already know how to move 4. So take the top 4 disks, move those off to the 3rd post, and then move the largest disk to the middle, and then take those top 4 disks from the 3rd post and move them to the 2nd. So this is a recurrence relation, right? If you know how to move n disks, you know how to move n plus 1 disks. Just move the first n to the 3rd post, move the biggest disk to the middle, and then move the n disks from the rightmost post to the middle. So let f of n equal the number of moves required to move n disks. Well, if you want to move n plus 1 disks, what do you have to do? You have to move n disks, right, the top n disks from the first post to the 3rd post, and that's going to require f of n moves. And then you have to move that largest disk to your destination, and then you have to move those n disks from that 3rd post back to the middle, which is going to take another f of n. So there's a recurrence formula for f of n plus 1. It's twice f of n plus 1. And if we only have one disk to move, that just takes a single operation. So there's our base case, there's our inductive step. And so if we think about some values for this, f of 2 would be 2, f of 1 plus 1, which is going to be 3. F of 3 will be 2 times 3 plus 1, which is 7. F of 4 will be 2 times 7 plus 1, which is 15. And so it looks like moving n disks takes 2 to the n minus 1 operations, best case, using this algorithm. Yeah?
Can you compare recurrence and recursiveness?
They're the same thing, basically. Recurrence relation is something like this, right? It's expressing something in terms of earlier versions of this, but that's basically what we do with recursion. Right, we do a merge sort on 10 pieces of data by doing a merge sort on 5 pieces of data. Right, so this is the same idea as what's going on in recursion. So we can use this relation to calculate how many moves it takes to relocate n disks from one post to another, and it looks like it's 2 to the n minus 1. So if we have 64 disks, 2 to the 64th minus 1. So that's a big number. And if you do 1 disk a second, that's a really long time for the universe to live. Probably longer than it actually will survive. So we're not in danger. But in doing this analysis, right, this idea that we can move n plus 1 disks by first moving n, and then moving the biggest disk, and then moving n again, embedded in that analysis is the algorithm for actually solving this problem, for actually doing these moves. Pick up these disks, move them, move the biggest disk, and then move that pile again. So we can spin some code for this. Let's do 4 disks. So I'm writing a recursive function called tower. And tower takes 4 arguments. The first is the number of disks that you have. Okay, so we'll do this for 4 disks. And then the peg that you want to move from, 1, 2, or 3, so we're starting on peg 1. We're trying to move to peg 2. And then I'm telling it what the free post is. In this case, it's post 3. We could find that from knowing we're using 1 and 2, but I'm just passing it. Source post, destination post, and then the free post. And I'm going to call tower, and tower is going to print out a solution. And I'm going to use a global called moves to keep track of how many moves it took. Okay, and I'm going to print that out at the end. Okay, so what does our tower function look like? I'm going to increment the number of moves, just to keep track of that. If you're only moving 1 disk, I'm just going to say move it from the from post to the to post. Okay, that's our base case. Move 1 disk, just move it from to to. And my move function is just going to print out a message saying move it from this post to that post. Okay, so it'll give us the instructions. Otherwise, I'm going to move num minus 1 disks from the from post to the open post, okay, that third one. And then I'm going to move 1 disk from the from post to the destination post. And then I'll move those num minus 1 posts from the open post to the destination post. So that's my whole tower function. Right, if I only have one disk, just move from the source to the destination. Otherwise, move num-1 disks from the source to our third post, move the biggest disk, and then move num-1 from the open post to the destination. And this move function is just a print statement. I'm just going to print out the from post and an arrow in the to post, and I'll print out 5 per line. So if I do this for 4 posts, there's the instructions. So let's try this. You don't get to see this at home. This is your benefit for being in class. So we move from post 1 to post 3, post 1 to post 2, post 3 to post 2, post 1 to post 3, so this is 1 over here on the left, and then post 2 to post 1. So we've done our first 5 steps. Post 2 to post 3, 1 to 3, 1 to 2, and so that should be the halfway point now. And then from 3 to 2, and then from 3 to 1. And then our last 5 steps go from post 2 to 1, post 3 to 2, 1 to 3, 1 to 2, and then our last step go from 3 to 2. Ta-da. This would be a cool SLP. To like do this with magnets that like make these things float and move around. It'd be like really awesome. Alright, and it kept track of the number of calls to tower and it gave us 15. So if I just call towers with 8, there's a solution for 8. And it's 255 moves. But if you follow this, right, that will move the whole stack of 8 disks.
Can you do it with 64?
You want the universe to end?
Yes.
There you go. Start moving. So there's the solution for 64 disks. It's going to be a really long time before it finishes, even if we were keeping up with it. Right? But, you know, it's got no problem coming up with a solution. The recursion doesn't get very deep.
There was no dynamic programming for this, right? Like you could, but this.
You could. I mean, you could solve, we're ending the universe while you were gone. So there's the solution for 64 disks. You could, so because we're moving, we're solving the problem for n-1 twice, right? So we could solve it once and then we could save that solution. But the time it takes to actually go down and calculate the solution is not the big issue. It's really what we're doing with it, whether it's printing it or moving disks or something like that. But yeah, we could theoretically speed it up. Don't tell the monks. So that's a nice application of recursion.
How long is it gonna take
Well,
in the universe?
2 to the 64th, how quickly you want to move disks.
It'll probably take 2 minutes.
There was a long period of my life where I spent a good part of my days and nights doing these calculations and then trying to convince other people of these. So I have no objections to running numbers like this. So 2 to the 64th, not a huge number. Let's say it takes you 1 nanosecond per move. Okay, so you can do 1 billion disks per second. So 2 to the 64th over that That's how many seconds it's going to take. 3,600 seconds to an hour, that's how many hours. 24 hours in a day, that's how many days. 365 days per year. 584 years. That's if you're moving 1 billion disks a second.
I think that's doable.
That's probably doable. We could have a 600-year battery, right? Now, if you're moving 1 disk per second, it's 584 billion years, and then we're pretty high out there. It's still going, that's good. We should have a progress bar. Universe ending in 98%.
Get stuck at 99% for.
Exactly, yeah. All right, so questions, comments?
I have a question on progress bars.
Okay. Why are they always so horrible?
Huh?
Why are they always so horrible?
Yeah, like what do they, like,
Yeah.
what is the progress?
Yeah. It depends how you're measuring it, and a lot of times I think applications are using progress bars when they have no business using them.
Okay.
I don't know, you're trying to save a file to disk. That's what you're always doing in movies. You're trying to get your flash drive back before whoever's coming after you comes through the door. So you're saving the disk, and it's like counting up and counting up. Well, you're probably, saying there's 1,000 files, and I've done, 900 of them, so we're 90% there, right? But, there's overhead. There's not all files are the same size. There's other things that kick into the system that affect your load. There's all kinds of things. My feeling when I'm encountering progress bars that annoy me is that they're using a really crude metric, like how far are you through the file, and they're ignoring the fact that when you get to the end of the file, then you have to do this other huge operation, which was too hard to take into account or something like that. But I don't know. That's probably one of the mysteries of the universe. But this one would be pretty easy, right? Because we know how many steps it's going to take, and each step is taking basically the same amount of time, right? But if we were going really deep with recursion and we were running out of memory and it was getting harder and harder to do the mallocs that we needed to allocate more memory, this would start to slow down, right? And if I just had a progress bar that said you've done half the cases, you're 50% done, that would have that same annoying, slowing down as it gets closer to 100 kind of behavior. All right. Other questions, comments? All right. Well, it was like some graph theory. But I want to move on to languages and encounter again chances are you'll take so this is we use to communicate with one another. See, informal, like I'm going to talk about syntax. Analyze the semantics of involved tasks. Analyzing the syntax equals a noun phrase. Verb phrase. Is an article by a noun. Or perhaps just an is eats. For example, an article followed by a noun. Noun phrase. So I know that because an article can be the word All right, this is where Mad Lib. All weird, right? But the syntax. Construct sentences from this and analyze a sentence. Non-empty set. So lambda is the empty string. It's a string whose all the words over V. Set sitting side by side. collection of strings. Over V, every possible combination of that gives you a complete specification. And it was like the unabridged super. And if it's not, you got a syntax error or something. For example, if you have the word, that's got a Q. So grammar, general. So not a set. Big B and A. A. be replaced with two Bs. So this is a collection of symbols. R is some then um, was AB. Single rule that changes S into this. The language symbols. S goes to a little algorithm that we as humans use to start symbol. What's the string? Big A, and that says we can change so that one's not too bad. So form yeah, it's a selection of terminal symbols. We can derive from S. So be replaced by two ones followed by there's an infinite number of words in this language. A phrase structure grammar with I want to look at some more interesting cases. Hasn't ended.